the more amount of games you play, then yes, you would be. I mean, that would be. Yes, it would be justified that you'd be more
I
likely to
could
win if
not
you
hear this
challenge
nigga
denied.
talk.
Yeah, no,
That's why I called it a
yeah,
gambling fallacy.
that nigga Madoka, he doesn't know what he's talking about. He's a fucking idiot. Because when we're talking about Bayesian updating, or we're talking about a mathematical framework for rationally updating beliefs about dependent or uncertain events using prior probabilities and new evidence. For example, it would say that after observing 10 heads in a row, I update my belief that the coin might be biased. And unlike the gambler's fallacy, when we're using that type of reasoning, it explicitly models dependencies if they exist and quantifies the uncertainty. So the key differences between the two would be when we're talking about gambler's fallacy, the assumption would be like an incorrect assumption of independence is broken. But when we're talking about Bayesian updating, it explicitly models dependencies.
Why not?
If
Why don't
present.
you use the dice? Why don't you use this dice example? If you will roll a dice and you kick 99 times, it's a
Okay,
probability.
you have nothing to, like, informative to offer.
Why did he get disconnected?
So when we're talking about probability structure, a gambler's fallacy would ignore true probability, for example, a fair coin. But we're talking about Bayesian updating, we incorporate prior knowledge, for example, coin fairness. And then we're talking about a gambler's fallacy again for the rationality, that would be like a cognitive bias, like it would be irrational. But for Bayesian updating, as I said earlier, we're using a mathematical framework, which is rational. So to simplify this shit down, a gambler's fallacy would be, well, tails is due after 5 heads, but Bayesian updating would say, well, 10 heads suggests the coin might be biased. So we talk about like a context of dependence. In Bayesian updating, it's only fallacious if misapplied to truly independent events, like assuming a fair coin becomes biased after like a streak. However, in cases where dependency might exist, for example, like a possibly rigged coin, Bayesian updating is valid. For example, we would have the prior belief that 99% chance the coin is fair, and after 10 heads, the posterior belief shifts towards the coin being biased. So then when we're using the Bayesian method, we'll start with a prior probability, which is the most coins are fair, and we'll use likelihoods, like how probable is 10 heads with a fair versus a biased coin. So then we update our posterior probability given the data that the coin is likely biased. So that is going to be rational if the model accounts for possible dependencies. But in contrast with the fallacy, the gambler's fallacy ignores the independence, which is the tails is due for a fair coin, and the Bayesian updating tests for independence, like does a streak suggest the coin isn't fair. So we would have like a concrete example, like a scenario where a coin lands heads like 10 times in a row, and the gambler's fallacy would be, well, the next flip is most likely to be tails. And the error in that assumption would be, you'd be assuming the coin owes the tails, ignoring the independence. And the Bayesian updating will say the prior is 99% chance the coin is fair. It's like 50-50, because that would maximize entropy. And the likelihood of 10 heads with a fair coin will be like 0.5. And then we'll say the posterior adjusts the probability that the coin is biased. And the result will be a rational belief shift, not a claim that the tails is due.
Right. I know. Yeah, I get the same. If it's not, yeah, if it's that, then to my knowledge so far, I don't have a problem with it.
All right, word.